Okay, so as we move on here, we're going to take another look at locations of spread. Today we'll focus on the standard deviation. So if you do remember in our last session, if you do remember in the previous video, I showed you these two different distributions of wages that you could get at two different high street supermarkets. It was difficult to tell or distinguish the difference between them because they both had the same mean and they had the same total. The deciding factor came down to a measure of spread, and in this case it was the range. The ranges were very different, which indicated their consistency. The consistency on the left hand side is high, we get the same wages every single month. The consistency on the right hand side was low because there is a large spread of different values we can get in our wages. So we looked at the range and we looked at the interquartile range. The range used extreme values. It used the maximum and the minimum, so it would always contain an extreme value if there was one. So to avoid using extreme values, we started to use the interquartile range, which still gave us some idea of how far spread the data was. Today, we're going to look at a more robust measurement of the spread of the data. We'll be looking at the variance, and the variance takes every single piece of data into account and should be the most powerful of our measures of spread. Okay, so let's just start with a definition. The variance is the average squared distance from the mean. So let's try and break that down. We'll start with some notation. The notation we use for the variance is sigma squared. Now the squared is very important. Variance will always have a squared on it. Well, how would we represent the distance from the mean? For every x value, if I subtract the mean, if I subtract x bar, that will give me the distance of that particular x value, that particular data point from the mean. So x minus x bar gives us the distance from the mean. But we need the squared distance from the mean. So let's put some brackets on there and we'll square it. And to build on that some more, we need the average squared distance from the mean. So if I add up all of these squared distances from the mean and divide by how many there are, that will give me the average squared distance from the mean. Okay, so that explains the formula and why it looks like this. Let's actually try and see it in action. Okay, so I'll start with a simple example. There's only two numbers here. If we find x bar, I hope you can do this in your head quite quickly. It's going to be 14 over 2, x bar equals 7. Okay, now let me find the distance from the mean, the distance between each of these values and 7. So let me go ahead and find the difference between the mean and each of these values. So each x value subtract 7, I'll get -4 and +4. At this point, some people would think, well, can't we just find the average of these distances? Can't we find the average of these differences? And it does seem like it should make sense, but if we were to sum up these differences, we get 0. That's because we use the mean to generate them in the first place. The mean was created from these values, and it was designed to be exactly in the middle. It was designed to have just as many values or just as much combined positive differences from it as it has combined negative distances from it. The mean was already the value where the sum of its differences would equal 0. So it's not useful to try and add up these differences right now. For those of you doing further maths, we'll look into something similar to this. We'll look into residuals and how far away data points are from a mean or from a line of best fit or from a regression line. But for now, let's just get back to calculating the variance. So if we can't sum these values, we'll instead square them. So at least when we sum them, we're not getting 0. Squaring them, we get 16 in each case. And at this point, I think I can use the variance formula. I'm going to try and find the average of these values. So 16 plus 16 divided by 2 equals 16. So the variance in this case is 16. The only problem we have here though with the variance is that it's not actually the same units as the original data. We've squared all of those values, so these are squared units. And sometimes a squared unit wouldn't particularly make sense. If this was £3 and £11, well now the variance is £16 squared. And pounds squared doesn't even make sense as a unit. So one more step that we can do to try and make the data sensible is to square root it. When we square root, we generate a statistic called the standard deviation. And now the standard deviation is a bit more understandable. It makes more sense in our context. If we were to square root, the standard deviation is 4. So 4 is a measure for the average distance of each of those data points from the mean. And it makes sense. We knew that the distances from the mean, we knew that the differences from the mean were +4 and -4. So on average, they are a distance of £4 away from the mean. Now in this case, we got the actual average. There are other instances where it's a bit more of an estimate of the average, but we'll still take the standard deviation and the variance as our indication of how widely spread a data set is. Okay, let's take a look at a slightly larger data set. So we've got 5 data items here. Lengths have been measured, and if we were to go ahead and find the mean is 4. Let's set up our table again. Here's all of the data points. The difference between each of these and the mean is going to be the x value subtract 4. So we generate some negatives and some positives. But once again, if we were to sum these and try to find the average, we would actually get 0 as the sum. So we wouldn't make any headway with finding the average. So we square them instead, and we try and work out an average from these squared values. If we sum the square values together and divide by 5, then we've generated the variance. So they add up to 16, divided by 5, 3.2. 3.2 is going to be in centimeters squared. So it's not a very good comparison to the original data. It's in the wrong units. So we find the standard deviation instead, which is the square root of everything else that we just did. And the square root equals 1.7889 to 4 decimal places. Okay, so we'll try and keep our answers rounded to 4 decimal places to maintain some accuracy everywhere we have that opportunity. Well, that was the rationale and the motivation behind the generation of that variance formula. The reason we use it, why it makes sense to use, and why we square root it to find a more usable statistic, the standard deviation. Now, there is an alternate version of the formula for the variance, and here it is on the screen. There's a proof of how this is equivalent, or how this is generated from our original version of the variance formula, and it is quite lengthy, but you're not expected to know this. Those of us studying further statistics, we will come across this, or at least make use of proofs just like this later on in the year. A benefit of this alternate form of the variance and standard deviation formula is that it actually contains some quite useful and easy to find summary statistics. If you notice, we only have 3 terms that we might need to find: the sum of x squared, the sum of x, and an n value. Now, n's should be quite easy to find. It's the number of items involved in the dataset. The sum of x, we just need to add together those values in the dataset. And the sum of x squared, we just need to square each number in the dataset and then add them together. And these can just be placed into the formula quite easily. This extends to frequency and grouped frequency tables, where we have the sum of fx rather than just the sum of x. We have the sum of f rather than just n, but the sum of the frequencies was always going to be the number of data points involved. And also we have the sum of fx squared, which is equivalent to the sum of x squared. When you do come to use your calculator to generate some of these summary statistics, your calculator doesn't display any of the F's. So your calculator screen will just display sum of X, but you need to know that since you are working with a frequency table, that is really the sum of Fx. Your calculator won't display the sum of F, it will display N. And the sum of Fx squared will simply be the sum of X squared. We'll look at that a little bit more in detail when I show you how you can generate these on a calculator screen. Okay, let's revisit those two examples. So firstly, 3 and 11. I can generate these summary statistics. N equals 2, sum of X is 14, sum of X squared, 130. X bar is still 7. So if I was to calculate the variance, I'll just need to substitute these values into the formula. I'll take a quick second here just to point out that the bracketed expression, sum of X over N, is simply X bar. So if you've calculated X bar previously in a question that you're attempting, you can actually just substitute the found value. The only time I wouldn't do this is if you'd rounded your X bar. I would then put the original values in just to make sure we're maintaining accuracy in our final calculation. So let's substitute the 130, the 14 and the 2 into your calculator. You get an answer of 16, just like we did before. And the standard deviation, the square root of 16, you don't need to calculate for this. That will simply be 4. So the standard deviation and the variance we actually found as long as we knew those 3 pieces of information, those 3 summary statistics. Some questions give you summary statistics at the beginning, and it really is just about making sure you know how to place these into the formula. Let's move on to the second example where we had 5 data items. The sum was 20. The sum of X squared, each item squared and added together, was 96. And X bar once again was 4. So we have the pieces of information that we need to place into the formula to generate the variance and the standard deviation. So we're going to have 96 over 5, subtract 20 over 5, all squared. And that gives us a variance of 3.2. Okay, don't forget we'll need to square root that to calculate the standard deviation. And once again, the standard deviation 1.7889 to 4 decimal places. So with those 3 summary statistics, we can generate the standard deviation and the variance. Okay, so let's see how we can put that into action. If we bring out our calculators to try this grouped frequency table, and just take a second to take it in and think of all the key aspects we need to consider before we make a start. So firstly, there are gaps between these intervals. The class limits have a gap in between them, and we need to be sure to use the class boundaries. So we're going to use the upper and lower bounds of the class limits to generate class boundaries. That's the first thing that jumps out to me. Secondly, I've been given a summary statistic in the square brackets just underneath the table. That's going to be useful for me to check that the summary statistics I generate are actually accurate. Okay, so let's get out our calculators. We're going into menu 2, the statistics menu, and we're going to input midpoints, and we're going to input these frequencies. As I said last time, if you're not sure that you're calculating midpoints correctly in your head, you can actually put in the calculation. So the lower class limit plus the upper class limit in brackets divided by 2, and the calculator will find the midpoint for you. So 21 plus 25 divided by 2, 26 plus 30 divided by 2, etc. So the calculator generates these midpoints. We can add in these frequencies. I want you to double check if you've set your one variable frequencies to list 2. You should only need to do this once when you first get your calculator and anytime you've reset your calculator. You don't need to do it for every calculation, but I'll show you again just in case. So we'll go over to the set menu. we'll just check one variable frequency. It will either be a 1 or it will say list 2. I want your calculator to always say list 2. Okay, now that that's set up correctly, let's go back and we'll calculate our summary statistics. Perfect. So on the screen, I can see my x bar, I can see the sum of x, I can see the sum of x squared, and I can see n. I notice straight away that my sum of x squared matches the sum of fx squared that they have on the screen. So I'm happy that we've input all of those data items into the calculator correctly. So from here, I can just put these summary statistics into the fraction and solve. Some of you are eagle-eyed and you may have noticed that actually our value for sigma was on the calculator all along. Our value for the standard deviation was right there in front of us. We can just write down this value, but there are many questions that are designed to make sure that we're using the formula correctly. There are many questions that are designed to only find the variance, where this is the standard deviation. So on those particular questions, the examiner is expecting you to use the formula. There are many questions that are designed where you don't get the original raw data, and you might have some summary statistics to begin with. And those are the questions that make sure you know the formula. So I recommend for every question, you are presenting all of the summary statistics in the formula as you should, and then you can write down the standard deviation next to it. This is to make sure you're ready for any variation on this type of question. Okay, and we're just about finished, but before you move on to some practice questions, let's take a quick look at the specification and exactly what it is that students are expected to be able to show, exactly what the examiners are anticipating you will be confident on. While you read through that, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date, maybe come back in 2 or 3 weeks or before an assessment. And as you watch through the second time round, because you've done your practice, a lot of what you go through here should resonate with you much more. And you have a chance to really embed your understanding of the difficult concepts, the ones that have been flagged up as A star.